class. Today I'll be talking about swinging rods. You may think of this as an application of all the ideas that we have so far considered. And I'm mainly thinking about things like energy and Newton's second law. The setting of the problem is fairly simple. I have a rod which is being held at a 90-degree angle and pivoted about point P, and we are to study the motion of the rod. A couple of questions I'm interested in answering. One of them would be what the speed of the rod would be when it comes to the bottommost point. So you must think of this as a pivot, and this rod is swinging freely coming down here. What would be the final angular speed? So that would be omega f. And at any given moment of time, let's imagine that the rod is at some intermediate position alpha, theta. Theta is the angle. And let's take this angle to be this angle here. At any intermediate position, I also want to find what the angular acceleration would be. So there are a couple of ways of doing this problem. Also, I want to make this problem a little more interesting than just a uniform rod. So I'll take this rod to be a non-uniform rod. That means it's got a mass distribution that's not linear. That's not constant, lambda equals lambda naught would be a uniform rod, but here I'll take it to be some constant a times x squared, where the coordinate x is measured from P being the origin and x is being extended out here. Let's say the rod's length is L, so that would be x equals 0, that's x equals L, and we're trying to find what the angular acceleration is at some intermediate stage, and also what the final angular velocity is. So this problem is pretty routine, because we've already seen how to do the various things in previous videos. So for example, if you watch the videos on center of mass and moments of inertia, this is just an application of those ideas that you saw there. So we'll call this dx, and the definition of lambda, remember, is dm over dx, and so that's going to be ax squared. So you can solve for dm, it's just ax squared dx. So you can get a number of things quite immediately. So first let's find the mass of the rod. I'll just call it little m. It's the integral of dm. So that's going to be the integral of ax squared dx. X equals 0 to L, and so that's ax cubed over 3, and when you evaluate it, it's al cubed over 3. Well, the second thing you can find is where the center of gravity of this is located. So we'll call the center of mass location x bar. Bar is sometimes used to denote the center of mass location. Instead of x sub com, it's easier to write bar. So this is, by definition, integral of x dm divided by the total mass, integral dm. Well, the integral of x dm means I just take this dm here and multiply it by another x. So that's going to be the integral from 0 to L ax cubed dx. And this we already know, it's just what we found in the previous step, so I'll write it down. Evaluate this integral next. Well, the integral of ax cubed is ax4 over 4. and when you evaluate it, it's AL4 over 4 divided by AL cubed over 3. The A's cancels, L cubed cancels with L to the power 4 there, leaving us with just 3/4 L. And the last thing we can find is the moment of inertia about the pivot point P. Well, that by definition is the integral of x squared dm. It's r squared dm, where r is equal to x in this case. X would be the this coordinate here, where the mass element dm is currently located. So let's evaluate this next. That's going to be the integral from 0 to L. When I multiply dm, which is that, by an x squared, I get ax4 dx. And when I evaluate this, I'm going to get ax5 over 5. So that's al5 over 5. So that's all the calculus we really need in this problem. Now let's look at the rod at any given angle position. We're going to have the free body diagram. There's going to be just one force, which is the force of gravity, the total mass of the rod times the acceleration due to gravity, and that will be acting a distance x bar away from the pivot. So we can find the torque and write Newton's second law. So let's write Newton's second law to find the acceleration. The sum of all the forces, the torques about P is going to be equal to I sub P times alpha sub P. So the torque is the distance times mg times sine of the angle between r and mg, which is just theta. So also notice that alpha is into the page, so I'm going to put a negative sign for that one. Negative sine mg x bar sine theta is equal to I sub p times alpha sub p. So I can immediately figure out what alpha p is. Alpha p is equal to negative mg x bar sine theta over I sub p. So this gives us the angular acceleration at any given angular position theta. So I want to actually use this to find out the final speed. And then we're going to confirm our answer using the energy method. So how do I proceed to go from here to find the final velocity? Well, there's a little trick involved here, and that trick is the following. I can write alpha, which by definition is the rate of change of omega. If you go back to my rotational variables video, that's where you saw this. Well, there's a funny way of writing this using the chain rule. I can write this as d omega by d theta times d theta by dt. Well, d theta by dt is just omega, so that's going to be omega d omega by d theta. So I can multiply both sides by d theta, or mathematicians like to call it taking the differentials of both sides. That's going to be alpha times d theta. So I'm going to be using this result along with equation 1. So let's try to substitute for alpha sub p over there. If I integrate both sides now, integral of omega d omega is 1/2 omega squared. And well, initially it was not moving, so the initial condition is 0. So we don't have to worry about that. And that's equal to the integral of alpha d theta. Now when I take the integral of this, m will come out, g will come out, I sub p will come out, x bar will come out, and the only integration variable is sine theta. So this will be omega f over there. So this is from 0 to omega f, and that angle is from 90 degrees all the way to 0 degrees, because as this rod swings, the angle keeps decreasing. So this gives me negative, all these constant terms I can bring outside, and I just have the integral of sine theta d theta. Well, the integral of sine theta is negative cosine theta, so that will take care of the negative sign up here. And I'm going to get 1/2 omega f squared equals mg x bar over I sub p cosine theta evaluated between the limits. The lower limit does not contribute because cosine of 90 is 0. The upper limit contributes, and that's cosine 0 degrees, which is 1. So I'm going to get omega f is equal to 2 times mg x bar over I sub p, the whole thing square root. So that's the answer, and let's substitute some values inside. 2 times the mass is given by al cubed over 3 times g. X bar is 3/4 L, and I sub p is al5 over 5. Let's see what simplifications occur. The a cancels out, 3 cancels out, there is a 2 that goes here. There's an L to the 4 in the numerator and an L to the 5 in the denominator. So when the dust settles, that's going to be 5 halves g upon L. So that's the final angular speed. Now I want to confirm that this angular speed is exactly what I would have got had I used the energy method. So in the energy method, what one does is we look at the initial energy. Well, that initial energy is all potential, and the final energy is going to be all kinetic. So the potential energy lost is going to be mg times x bar, and the kinetic energy gained is 1/2 m omega squared. So let's try that as a confirmation of what we've just done. Okay, so here's a check. And the check would be loss of potential energy is equal to gain in rotational kinetic energy. So the loss of potential energy is mg x bar, and the gain in rotational kinetic energy is 1/2 I omega f squared, because initially there was no rotational kinetic energy. If you take the square root, this is I sub p. I get omega f equals 2 mg x bar over I sub p, which you will notice is precisely what you had here. So the two answers match up, and all is well with the world. You can do this problem in either the energy method, which you'll notice is not that much different in terms of the total work involved than the torque method. The torque method does involve this little trick, but once you know that trick, you can do it both ways. There's no it's not like one method is superior to the other method. You can do it both ways. So that was the example of a swinging rod that had non-uniform density, and you can I did it using both Newton's second law and by using the energy method to confirm it.